Elementary event. So what is an elementary event? So let's see an elementary event with its own definition and a few of the examples. So elementary event is an event which has only one outcome is called an elementary event. For example, picking a red ball from a bag containing 6 balls where 2 red, 1 blue and 3 white balls. So in this bag containing 6 balls, there are 2 red, 1 blue and 3 white balls, where picking a red ball from a bag is an event which has only one outcome, that is picking only the red ball. So the outcome here is a red ball, in which we call as elementary events. So this is one of the examples through which we understand the elementary events. Say for example, I take a dice, and in this dice I want to get getting a value less than 3 on its top, that is on the top of the surface of the dice, is not an elementary event, because if I want to get a value which is less than 3 on its top, the possibility is I may get a 1 or a 2, not a 3, because less than 3. So the possibilities are I may get a 1 and 2, which is not, that implies more than one outcome. So in case of these kind of problems, the outcomes are more than 1, where I have 1 and 2. So more than one outcome, and hence getting a value less than 3 on its top is not an elementary event. So this is not an elementary event. So like this, we understand the difference through identifying the number of outcomes in the event or the conducting of the event. So picking a red ball from a bag is purely an elementary event because there's only one outcome of picking up only the red ball. For getting a value less than 3 on the top of the dice is not an elementary event because we can get 2 values, either 1 or 2, when I say less than 3. So there are 2 outcomes which makes us contradict the definition, and hence throwing of a dice and getting a value less than 3 on its top is not an elementary event. 2 outcomes, 1 and 2, is how we understand the elementary events. So let's see what is the mathematical relation in identifying the relation between each of the elementary events mathematically. Let's construct this and understand this more better through an example problem. So to start with an example problem, let me consider a bag which contains totally 8 balls. So this bag totally contains 8 balls, out of which 5 are blue, 2 are yellow, and 1 is white. So these 8 balls have 5 balls which are blue in color, 2 are yellow in color, and 1 is white in color. Now I have 3 possibilities where I want to find the probability of each of the color. Say for example, in the initial case, I want to find the probability of getting a blue color when I pick the ball from the bag containing 8 balls. So clearly, probability of picking the blue ball is total number of balls, which are 8 in number, and the number of blue balls, which are 5, which comes here. That is, the number of outcomes is number of blue balls which I can pick, which is 5, and the denominator is total number of outcomes, that is totally 8 balls which come in the denominator. Similarly, the probability of picking a yellow ball, let me see what is the outcome. Totally, there are 8 balls, out of which I can pick 2 yellow balls. Therefore, this comes out to be 2 over 8. Thirdly, the probability of picking a white ball from the whole bag is 8 on the bottom, and then there's only 1 ball which is white which I can pick, the outcome being 1. The number of outcomes favorable to the event E of picking a white ball is 1 over 8. So each of the elementary events here are identified as picking a blue ball, picking a yellow ball, and picking a white ball. So for these 3 elementary events, let's see what is the mathematical relation connecting the elementary events. Interestingly, as I see these 3 values, I just try to add them and see what is the outcome. So when I add each of the values of the 3 elementary events, I get 5 over 8 plus 2 over 8 plus 1 over 8, which on simplification gives me 8 times. So on this consideration, I get 8 as the LCM, and then I get 5 plus 2 plus 1. This on further simplification gives me 8, 5, 6, 7 and 8. Therefore, this gives 1. So what does this make us understand? This experiment or this example problem makes us understand that sum of all the probabilities of elementary events is always equal to 1. So I come to the conclusion that in this case of the problem, which is universally true for any of the problem which is taken with elementary events, I finally conclude that sum of all probabilities of the elementary events of an event E is always equal to 1, is how we conclude the formula. Sum of all probabilities of the elementary events of an event E is always 1. So sum of all the probabilities of elementary events is unique, is how we understand the uniqueness of the probability connected with elementary events. The mathematical relation out here. So let's see what are complementary events and their respective probabilities. Complementary events are the events which are quite opposite to each other. That is, getting of a head when I toss a coin, then its complementary event is getting of a tail, because the other side of not getting a head is how we understand the complementary events. So here I identify the complementary events through occurring and non-occurring, or happening and non-happening. Happening and non-happening of an event E. So this is how we differentiate between happening plus non-happening, is how we understand the complementary events. They are said to be complementary to each other. Say for example, I take probability of getting a head when a coin is tossed is 1 by 2. Then the probability of getting a tail when a coin is tossed is also 1 by 2. But I can say this is 1 minus probability of getting a head. We identify the complementary as 1 minus probability of getting a head, which is found to be half. That is, I get 1 minus half, which is 1 by 2, is how I get probability of getting a head and T. So here these two are complementary events. Therefore, if A and B are complementary events, probability of A plus probability of B is 1. So this makes me conclude, that implies probability of H plus probability of T is 1 in case of tossing of a coin. For tossing of a coin. Therefore, for any two events, complementary events are defined as for two events A and B, I have P of A plus P of B is equal to 1, then I say A and B are complementary events. Therefore, for complementary events, P of A plus P of B is always equal to 1. So when I say the two events are complementary, then this has to come in mind as the mathematical formula. So generally, the complementary events are denoted with general notation as in the following manner. Say for example, I say occurring of an event E is denoted with E, then I say non-occurring of an event I denote with E bar or E complement. Then in this case, E and E dash are complementary events, that is E and E bar are complementary events. Therefore, I have the formula P of E equals P of E plus P of E bar equals 1. That is, P of E bar is more taken as 1 minus P of E. To read in words, probability of occurring of an not occurring of an event is 1 minus probability of occurring of an event, is how we understand this mathematical formula connected with the probability. So there are two types of special events which we identify in the topic of probability. The two special events which we are going to discuss exclusively in the session are impossible events and certain events. So these are the two types of events which are called as special or trivial events. So these are called even trivial events. Now, what is special about impossible events? That is, when I take a situational problem, if there is impossibility, if it is impossible to find the probability, then we call that as impossible or the certain. Let's understand the definitions through the more exclusive examples. So here, imagine I take a bag containing 6 balls, out of which there are 2 red balls, 1 white ball, and 3 blue balls. Now in this case, the probability of picking a yellow ball out of this bag is impossible because however you search, you don't have a yellow ball inside the bag. You have 2 red, 1 white, and 3 blue. So this probability of picking a yellow ball is almost impossible. So picking off a yellow ball is 0 since the bag doesn't contain a yellow ball. Therefore, these kind of events are called impossible events where the situation goes totally out of possibility. Picking a yellow ball is being one of the case in this example problem. Therefore, usually for impossible events, P of E is 0, then we say the event E is impossible event. So for impossible events, P of E is 0 implies E is impossible event. So for impossible event, we have P of E equals 0. So let's see what is a certain event with a similar example. Say I have a bag containing there are 6 yellow balls inside the bag. All 6 balls are yellow in color. There's no other ball which is different colored in the bag. That means if I wanted to find the probability of picking a yellow ball, so every time you pick a ball blindly from the bag, you get certainly a yellow ball. You cannot get any other color because the only existing colored balls inside the bag are yellow. So probability of picking a yellow ball is certain, therefore it is always 1. In this case, we say the event is certain because however number of times you pick the ball, it is always yellow in color. So probability of picking up the yellow ball is 1. So in such cases, we have, since the bag contains all yellow balls, unlike the previous case where the bag doesn't contain a yellow ball at all. So in this case, I have P of E equal to 1 implies E is certain event, is how we understand the difference between the impossible and certain events. P of E equal to 0 implies E is impossible event mathematically. P of E equal to 1 implies E is certain event with their own respective mathematical formulae. So the certain event here is also referred sometimes as the sure event because it is sure to happen. We call that as a certain or a sure event if P of E is 1, is how we understand the two special events in probability. Now in the session, let's see the range of probability. We need to understand the range of probability in understanding the values through their general understanding of probability. So let's recap with the definition of probability. To start with, we have for any event E, we have probability of E is NE by NS, and NE is number of outcomes favorable to the event E, and N of S is total number of possible outcomes. Therefore, we see that in this case, at the most, N of E is always less than, at the most being equal to NS. We see that this is less than or equal to this clearly. That implies N of E by N of S is always less than or equal to 1. That implies N of E by N of S, which I brought to the left, is nothing but P, which I'm going to substitute in terms of this. So this being P of E is always less than or equal to 1. Also, I identify that probability cannot be negative. So at the most, P of E is greater than or equal to 0, since chance cannot be negative. The chance of tossing of a coin cannot be negative because we can understand that through the general understanding of the probability or the chance of happening and not happening. Therefore, P of E is always greater than or equal to 0, and this is less than or equal to 0. Therefore, connecting both of them, I have 0 less than or equal to PE less than or equal to 1 is what I get as the range of the probability always lies between 0 and 1. It does not cross 1 on the right or does not cross 0 on the left. Therefore, if I take it on the number line, I have the probability which lies between this, including 0 and 1. So probability of E always lies between 0 and 1, inclusive between. It doesn't lie outside of 0 and 1. Less than 0 or greater than 1 is how we understand the range of probability. At the most, here I get impossible event because P of E is 0 at this point, and at the most it is 1 if it is a certain or a sure event, is how we understand the range of probability. Impossible event and certain event and the range of P is how we understand through the basic definition of probability as NE by NS. So now that we have discussed about the probability and few of the example problems connecting the definition of probability, let's see the learning outcome of what we have learnt about. Now we have seen different probabilities, the different situations or the different events gave us the different values of probability. Now let's come back to the question on why the international cricket matches use tossing of a coin for deciding on the batting or the fielding, the bowling decision, which is taken generally by tossing a coin. Why is it that tossing of a coin is taken as the chance of deciding which team wins and which team loses? To identify this, let's come with tossing of a coin and see why it is used through a more mathematical, valid understanding and justification. When I toss a coin, I have seen clearly in my previous activity of tossing a coin, initially I got the head, and in the second chances I got the tail. So my probability when the event is tossing of a coin, then probability of getting a head was 1 chance out of 2, and my probability of getting a tail is 1 chance out of 2 equally. That is, in this case, the percentage of chances is half times 100, which is 50%, and in this case also I get percentage of chances is half times 100, which I get to be 50%. So the winning and losing or getting ahead and not getting ahead has equal chances in case of tossing of a coin. And because of the equal chances of either teams winning on getting a head or a tail, or winning on deciding on the batting or the fielding session, is decided on equal chances, and hence the international cricket matches decide on tossing a coin for deciding on whether the team wins or loses through equal chances. So this has come because of the equal chances is the answer. So this is one of the learning outcome, or there are many learning outcomes through which we can estimate things through the probability connected with mathematics or daily life. Now let's take this example problem of playing of a cards. We all know the rules in the playing cards, where there are totally 52 cards on the whole in the playing cards. Now this question is about drawing an ace from the 52 cards, a well shuffled pack of 52 cards. I need to pick an ace, and we need to know the probability of picking an ace and not an ace for this given problem. So let's see how probability can be applied in real life now that we have learned all the topics of probability. Now coming to this, initially we need to identify the event E. The first thing we need to do in case of these word problems is identify the event E. As clearly seen here, we have that it is about finding the probability that the card is an ace, then my event E is picking up an ace, is how I understand the event E. Now total number of cards usually we know are 52 in number. Now in the entire 52 cards, I know that number of aces are 4, is the knowledge I need to have in the playing cards. Therefore, the number of aces is 4 and total number of cards is 52. Then picking up an ace, which is probability of E, is total number of outcomes are 52, because I can pick any card out of 52 cards in 52 different ways, or 52 times I can pick the card out of all the playing cards. Therefore, total number of outcomes is 52, and number of outcomes of getting an ace is 4, because total number of aces is 4 which I can pick on the whole from 52 cards. So therefore, because event is picking an ace, there are 4 outcomes of getting an ace is how I understand the probability. This clearly gets cancelled to be 1 over 13. Therefore, probability of getting an ace is 1 over 13. It's quite simple. That implies probability of getting an ace is 1 over 13 is how I understand this problem. Secondly, my question is about what is the probability of not getting an ace, and this question makes me understand or recollect on the complementary events which we have discussed in the recent sessions, because happening and not happening or occurring and not occurring are always connected through the complementary events, where P of getting an ace and probability of not getting an ace, the sum is always 1, the definition of complementary angles. So let's see how we can find the probability of not getting an ace as connected with this.